We start right now, sir.
Oh, just a minute. Yes, we are live. Can start.
Yeah. So, hi everyone. I'm Amar Mohammed, a mechanical engineering professor at IIT Madras and a manager at Alumni Relations Cell. I welcome you all to yet another wonderful session of the Guru Talks conducted by IIT Madras Alumni Association. Today we have with us Professor Sathyan Subbiah. He did his BTech in mechanical engineering at IIT Madras and went on to do his MS at University of Illinois and PhD at the Georgia Institute of Technology. Presently, he is a faculty in the Department of Mechanical Engineering at IIT Madras, and his research interests are in manufacturing science and engineering. His talk today will be majorly focusing on his recent endeavor, which is extraterrestrial manufacturing. He recently teamed up with a group of faculty and proposed a group called Extra-Terrestrial Manufacturing to focus on developing technologies for manufacturing in space. Before moving on to the session, the audience are requested to put any questions they have in the chat box, which will be answered by Professor Sathyan at the end of the session. So let's welcome Professor Sathyan Subbiah. The stage is all yours, sir.
Great. Thank you very much, Amar, and thanks to the Alumni Office for arranging this as well. I'm just going to quickly share my screen. 1 second. Yeah, I hope you can all see my screen. First of all, greetings from IIT Madras, and this is a great opportunity for me to communicate with all the alumni out there. I'm very excited today to talk about a new venture that we got into, which Amar already alluded to earlier, the Extra-Terrestrial Manufacturing Group, which we formed sometime earlier this year. So I'll just introduce you to this concept and what we're trying to do here. Yeah. Okay. So this is going to be the main focus of my talk: extraterrestrial manufacturing. Okay. Okay, so this is roughly the plan for talk. I think I've been allotted 45 minutes or so. Hopefully, I can cover this in that. So we'll talk about what is ExTeM, the group that we are trying to form here. I call it Make in Space, for Space and for Earth. I'll try to explain what that means. And of course, space poses a lot of constraints, including microgravity. So we'll talk about that a little bit, what it affects and how to get microgravity on the Earth. In fact, we have a nice drop tower facility at the campus that we are trying to make use of to get some microgravity. And then I'll talk a little bit about the projects that we're undertaking. I've selected a few only. I've not covered all of them. A couple of them I'll talk about in Make in Space for Space, and then a couple of them I'll cover in the Make in Space for Earth. And towards the end, I'll show you where we are compared to where the world is. And what's the direction that we should probably be taking it. Okay, so that's roughly the plan for the talk. Okay, so the first question is, what is all this ExTeM about, and why am I so excited about it? And what do you mean by Make in Space for Earth? Yeah. Okay. So ExTeM is a new initiative at IIT Madras. We grouped together, and the need for this came because, as you might have heard in the news, sometime in 2019, IIT Madras was awarded an institution of eminence status, which means that we get some funding, extra funding from the government of India, with the sole purpose of improving ourselves globally in the global presence, improving our global presence, and showcasing ourselves better. So under this umbrella, a year later, our director launched a sort of a mini competition within our campus. Where we said, okay, you guys can group together, write proposals, and then I would like to seed some of these groups, so to speak. So I remember, when we had India was still under the COVID's first wave peak. This was September sometime. We were all huddled up in our homes and then trying to have these e-meetings with groups of faculty, trying to figure out how to write proposals and so forth. So I coordinated this effort for this extraterrestrial manufacturing. I floated this idea around. A few faculty people got excited. So we met, we wrote the proposal. The proposal was sent out for peer review. So our director's office coordinated all this. And based on the review comments, they said, oh, this sounds like an exciting plan. And, let's seed some funds for this. So that's how we got some money to start this. So that's sort of how the birth of this ExTeM group is. And we were formally launched in February of this year. So we are about, 4 or 5 months old now. And we are taking a few baby steps to walk around here. So that's basically where we are at. So what is this? What did I actually propose, and what is this ExTeM all about? So I'm just trying to explain this in this cartoon here. So you have this Earth on the bottom left, and then the space on the top right here. These are all just cartoons taken. So there is this concept of making Earth for space, which has been around for a while. IIT Madras has been working a lot on this aspect. We've been working with ISRO. We have an IIT Madras ISRO cell as well here, for example. So these are stuff. What it means is that we manufacture and fabricate things on the Earth for use in space. So this could be, a simple example: satellites, rocket parts, various combustion activities that are going on in the campus, different manufacturing technologies that we have been working with ISRO for. But all this stuff is we are fabricating in the Earth, yeah. And then we launch it. ISRO launches it. It goes to space, and then it's utilized in space in various ways. Okay, and most of the stuff, it doesn't come back. It just gets used up over there. Yeah. Okay, so this has already been going on. We've been working with ISRO for a long time. So it's going on. So what we would like to focus on in this particular group is two aspects. One is make in space for space. So whatever we need to use in space, we manufacture and fabricate in space itself. While you're in orbit, while you're going on a mission to Mars or Moon, or you're on the Mars or on the Moon, So what kind of stuff that we can manufacture there and for use there? Yeah, so that's what I mean by what I mean by making space for space. Yeah. Also, another important aspect that comes about is there are things that you can make in space and bring back to Earth and use in Earth. Yeah, so there are good reasons why we want to manufacture and fabricate things in space. So these are the two things that the red color font shows: make in space for space and make in space for Earth is what we will actually focus on. This ExTeM group here will focus on. And the making Earth for space has already been happening in this campus here. So that will continue as well. And as I said, we have a nice cell that focuses more on this. Yeah. So this new initiative will focus more on making space for Earth and making space for space. Okay. So, with that in mind, the extra-terrestrial manufacturing, or ExTeM or ETM, as there's some two acronyms that are floating around. I proposed three verticals here: A, B, and C, as it's shown there. The box on the left side, which is gray in color, is what we will not focus too much on. Okay. So in terms of the vertical A, it will focus on manufacturing in space for space. And in that, we are sort of categorizing projects under two headings. These are very high level headings. Human settlement in planets, for example, which includes mining raw materials. So we want to make some unmanned robots that can do drilling, for example. And also, I have a colleague, Piyush, who will be trying to make use of Martian lunar soils to make concrete, for example. Without even water, can you make concrete, for instance? Yeah. So that comes under A1, human settlement in planets. So on the planet, you are making stuff, whatever you need on the planet, in the planet itself, so to speak, using the resources that's available in the planet. And then you have A2, which is long-term space flight onboard a space station or a ship. That is, you're traveling in a space station, and there's a need for stuff. The stuff can be stuff that is needs for repair. For example, electronics have failed, so you want to print electronics, or you want to have a medical diagnostic kit that needs to be printed there, for example, made there, or a bolt or a nut, or so many parts that are required, and you don't have the luxury of having a resupply mission coming to you from Earth. So making in situ things on board, and also involved in this is recycling. So recycling material on board. So these are two aspects. In fact, we have a lot of projects focusing on A2 in this vertical. And then you have vertical B, which is manufacturing in space for Earth use. So there are certain things that can be made better when there is no gravity, for example. So microgravity influences, gravity influences a lot of things. So for example, imagine you can take raw materials from here to space, we make things over there, bring it back to Earth, and then, look at it from a commercial angle as well. And some of those examples are, metal foams, crystals like diamond, for example, optical fibers, bioprinting, etc. Yeah. Okay. And these two pillars rest on this whole concept of microgravity tests that are facilities that are needed. So the vertical C will support both vertical A and B. Okay, so this is sort of how we have structured the ExTeM group. So some examples, and I'll spend a little bit more time on these examples a little bit later. So Martian concrete, I already mentioned, unbagged robotic drilling under this category of A1, which is human settlement. And long-term human flights, we're talking about 3D printing processes, using coating processes for diamond, for example, again, optics fabrication, maybe even medical diagnostics can be made in situ there. And recycling, recycling becomes a very important aspect. And the two projects that we're floating around in the vertical B is foams and diamond crystals. Yeah. Okay. And microgravity tests. So I'll talk a little bit about all of these verticals in more detail as we go along here. Okay. Okay. So before we go further, we have to understand, what is unique about all this, why space is so unique. I mean, space is exciting, yes, but what are the constraints it poses, and what are some of the aspects of microgravity that we probably have to sort of worry about as well. Okay, so let's look at the constraints of space one by one. So I listed about 5 constraints here. Obviously, the first constraint is space itself. What do I mean by space? That means dimensions. Yeah. So I mean, if you think of the International Space Station, for example, or onboard a space flight, for example, you don't have the luxury of a lot of volume, dimensions in space. Yeah. So it is whatever we have to make, whatever we have to send, etc., has to be small in dimensions. Yeah. We have to figure out how to make things work in a compact space, so to speak. Yeah. So that is obviously a major constraint. So here in the Earth, we have a luxury of I can build a big machine tool. I can have a lot of space here. I can do stuff that is not possible in space. Yeah. Okay. So we have to think about. We have to sort of rethink about how to reconfigure some of these machine tools and make them in a smaller dimension. A second one is energy. So obviously, the principal source of energy right now up in space is the sun. So you have solar panels deployed and so forth. But compared to what we can get in the here on the Earth here, the energy is limited there as well. So whatever machines we make, whatever processes we think of, has to be really energy conscious. So we have to sort of optimize towards the concept of energy as well. And of course, weight. If you're going to whatever we're going to send there is the one that we can use there as well. So and you have to launch it, and so there is no free launch or free lunch as a pun there. Okay. So we have to be careful of weight as well. Yeah. So anything that we have, any machine, any machine or raw materials, etc., it has to be weight conscious as well. The fourth important thing, which is also important on the Earth nowadays, is of course recycling. But recycling is very, very, very absolutely important in space because you get a lot of byproducts from various processes that we do there, and you can't just simply throw it out of the door. Yeah. So you have to figure out how we can recycle. You can always bring it back and burn it into the upper atmosphere when you come back, but that doesn't serve the purpose too much. If you're able to use them right after its primary use, then all the more better. Yeah. And of course, the last one and the not the least one is microgravity. Yeah. So microgravity can be good or bad depending on which processes you're looking at. So these are sort of the constraints in space. So we have to sort of rethink our whole manufacturing processes and machine tools that we've been using, machines have been using for various processes, whether it's 3D printing, whether it's machining, etc. From this point of from these sort of 5 constraints. Yeah. Okay. So if you think of microgravity and its effects, I'm sure this video, this is Sunita Williams, and I'm sure many of you have seen this video or similar videos in space. Yeah. So the effect of microgravity on fluids is obviously very clear, right? So it's fluids because of the surface tension effects, gravity, absence of gravity, they form a nice, they're not the usual liquids that we think of here on the Earth. They take up different forms, and the way you deal with them is differently as well. So that's very obvious. So microgravity obviously affects the fluids, its buoyancy, and so on and so forth. Yeah. Okay. The other things that that are affected by microgravity, materials, especially when you're actually synthesizing materials, and gravity plays a strong role, whether it is a foam bubble that is floating around or it's crystallization that's happening, for example. Materials, especially nanomaterials as well, gravity has a strong effect during its synthesis. Yeah. The other aspect that is very, very important is combustion, flames and fires, for example. So there's a lot of studies that are done on fires. And another aspect of where microgravity is having a strong influence is biotechnology. So if you're doing a bioprinting of organs, you're growing tissues, you're growing cells, gravity has a profound effect of it on the Earth. Whereas if you go up there, it can have a certain beneficial effects as well. And there are also some fundamental physics aspects that people are investigating. It could be a plasma effects. It could be various fundamental particles and so on and so forth. And also several nanoscale phenomena are affected by gravity. So in general, these are all various aspects that microgravity strongly affects. Okay, so I'll just quickly go through some of these aspects here. So some of the if you look at microgravity studies worldwide, and this has been going on for a while as well. So fundamental mechanisms that are affected with you switch on off gravity, what happens? Of course, assisting human mission in space, and now the work that we are doing for space manufacturing. And some of the active fields are listed here: combustion physics, fluid physics, material physics, and biomechanics. Okay, so here's an example of combustion science, and this is some of the work that has been going on in our drop tower facility here as well. So flames, so one of the major safety aspects on board a space flight is fire. Fire. Yeah. So if you're on board, there's a fire breaks out. There is no way for you to get out. Right. You're sort of stuck in the spacecraft. So there's a lot of work done on studies of fire. Yeah. So it turns out that gravity influences flames a lot, and how the flames would spread and so on and so forth. In fact, lack of gravity actually makes it worse. So people are trying to figure out how to overcome some of this as well, including, in fact, recently the group started a project on flammability studies for ISRO as well. And you have to figure out how to place sensors so that you can detect quickly how the flame is spreading and so on and so forth. Yeah. Okay. Fluid physics. I'll not spend too much time on this, but again, various phenomena of thermocapillary convections, multi-phase flows, heat transfers, complex fluids, etc., are also affected by gravity, and many such studies have been going on in this area. Yeah, the material science, solidification processes, crystal growth. If you're going to crystallize materials from a liquid state to a solid state, gravity plays a big role. Diffusion, process of diffusion, and can be in a gaseous form as well. Crystal growth does not have to be only from liquid form. So if you're having a vapor deposition processes, for example, crystal growth can happen from a vapor state as well. So, and the gravity plays a very strong effect on that. And then biomechanics and nanobiotechnologies as well as widely studied effects on microgravity. Okay, so for all of this to happen, of course, we have to have microgravity. Yeah, we can't all of us go to space and do the experiments, although some experiments are happening in space today. But achieving microgravity becomes a major challenge. Yeah. So here is a simple graph that shows on the y-axis here you have levels of gravity. Yeah. Okay. So you can see here 10 power minus 1 is about 0.1 g. Yeah. So we are on the Earth. You have 1 g. So this is talking about 1/10 of this g here, and this is about 1/millionth of a g, 10 power minus 6 g over here. Yeah. Okay. And on the x-axis is very important x-axis scale here, which shows you the time that the microgravity is available. Yeah. Okay, whether microgravity is available for a few seconds only, a few minutes, few hours, few days, few weeks, months, or years for us to do the experiment. Yeah. So, for example, if you take the space station, yeah, the International Space Station, all of you must have seen it in the news. You can get G's of 10 power minus 4 to 10 power minus 5. Yeah. Okay. And you can get that for months or years. Because the space station is going around, round and round, you can be there. You can do an experiment that can run for. So this is a very luxurious option, which unfortunately India doesn't have because we're not partners in the space station. Yeah. Okay. Whereas if you have something like an aircraft, like a parabolic flight, so you can climb into an aircraft. The aircraft will go through a certain trajectories, and that's some of it is shown over here. Okay. In that case, you can get up to 10 power minus 4 Gs. Yeah, but only for a few minutes here. We're talking about 15-20 minutes, something like that. Yeah, okay. Or you can have a sounding rocket, which gives you slightly better in terms of minutes range. Okay. Or if you have a drop tower, like what we have in our campus, you are talking about microgravity that will last only for a few seconds. Yeah. So I can get drop towers of 10 power minus 5, 10 power minus 4 Gs in the drop tower, but it will barely last for a few seconds. And I'm going to show you some videos that we took in our thing here. Okay. So if you really have to do experiments in microgravity and get benefit from this, you really have access to a lot of these platforms. Yeah. You could start with the drop tower. You could do a few experiments in the drop tower. You could move to a parabolic flight and get some few minutes extra. And then ultimately you want to go somewhere in the space station to be able to do experiments. And that's what all the countries are trying to do. We have one space station, which is a collaborative effort of many countries, and then you have several other countries that are trying to launch their own space stations as well, as you might have seen in the news also. Yeah. Okay. So this microgravity is achieving microgravity is will depend on two factors: the level of microgravity that you can get, how much of low G can you go, okay, and time that is it is available for. Okay. So those are the two important factors to remember. So what do we have here in our campus right now that I can, our group can make use of? We actually have a microgravity drop tower. Yeah. Okay. So this drop tower is shown here. This is a picture of the drop tower here. So as the name implies, we're going to drop something from the top of this, and it's going to fall through this tube down here. Okay. And then somewhere in the line, I'll get a micro G here. Okay. And it turns out that there are only about 6 drop towers in the world, and they're all listed over here. Okay, so Bremen, this is in Germany. Zam Bremen has a drop tower which can go up to 9.3 seconds, depending on the level of microgravity you're talking about. And NASA has a couple of them. Actually, in Glenn itself, they have a couple of them. There is one 5.18 seconds and one at 2.2 seconds. And China has one, Japan has one, and then we have one, which is 2.5 seconds. Yeah. Okay, so it's about a 30 plus meter free fall. You can get up to 10 power minus 4 Gs depending on how you design your capsule in capsule to capsule mode. At the bottom, to you don't want to crash your setup, so you have an airbag deceleration system, and operates in ambient environments. Yeah, and you can get only 2.5 seconds of micro G. Yeah, few seconds only. It's very small, but this is sufficient to do a lot of tests. It is not sufficient to do so many other tests, but there are some things that we can do with about a 2.5 second of a microgravity test. Yeah. Okay. So okay, I will maybe I'll skip this. Oh, okay, that is it does play. Okay, I'll skip this one here. So this just shows you details of the setup here. So this is the picture. If you see from outside far away, this is the setup on the far left. And if you zoom in here, you can see this is the top one where the IITM symbol is there. Is this guy on the top here? Then you have this long channel through which it falls, and then this green one at the bottom here is where your deceleration units are. Yeah. So what are we going to drop? We're going to drop what is called as a capsule. So the capsule is shown here. Okay. And within this capsule, we put all our experimental setups inside. So whatever, in fact, we are designing about 5 setups right now for various manufacturing processes, and they will all be sitting inside that. Yeah. So we have to figure out how to pack our stuff inside there. And the stuff means that our experiments and all the sensors that go along with it, it can be a high-speed camera, it can be a temperature sensor, it can be a pressure sensor, for instance. They all have to go inside. So to facilitate our arrangement, we have racks here. So some racks will remove, some racks will keep. We may have a power supply on board. We may have a DAC system to collect data and so on and so forth. And then on the top here, you have to have a mechanism to hold the capsule and then release it without any jerk so that it falls vertically down. And there is a hold and release unit that is there mounted on the top here. Okay. At the bottom, you have a big system, because it's just like a big airbag, actually, a huge airbag. You can see how deep that airbag system is. You can see the person here. So it's about three people tall, something like that. And then it has to be at the right pressure, and it has to deflate at the right pressure rate as well to prevent damage. Okay. Yeah. So the more details of this here, I'll show you some videos. So this is just actually just the deceleration unit alone. You can see how it is stacked down below the basement here. And it has the basic thing is an airbag. Yeah, so you can see some of the details. I'll show you a video later. So it has sand layers, foam layers besides the airbag. So there's an airbag on the top. Before that, there's a foam layer, and there's a sand layer finally to decelerate the units. Okay. Okay, so this is some of the actual setups you can see here. This is the actual capsule while it's open. You put your setup inside here, you close it, the cylindrical tube here, and then it is mounted up and then taken to the top, and it's now ready for drop over in this picture at the bottom right. Yeah, okay, so this is sort of what our system here is. Okay. So the system, as I said, includes, if you want to do an experiment, you have to measure stuff. So there's a measurement and a data acquisition system that is also available in that. Yeah. Okay, so this is some of them are wireless, so I can actually control some of this from outside in terms of data collection, starting some, the data collection, stopping the data collection. I can even trigger some things to happen remotely. So there is some wireless control as well. But this being only 2.5 seconds of microgravity, I don't really need to collect data and send it wirelessly. We actually store that data locally on board the system here. And then it will, at the end, after it drops down at the bottom, we just go down, we collect up the experimental setup, take the memory card out, and get all the data out. Okay, so there is some wireless and there is some wired networks as well. So here is an example of how this thing would probably do. So I'll just play this video here. This may be a bit choppy over the streaming here, but let's see. Hopefully, see. So this is so what you see here is this is the airbag down here. This is looking down the whole tube, yeah, the drop tube, and you see something at the top here. You can see here. This is the actual capsule. So this capsule will drop down all the way down to the airbag, and that's what we're going to see here. Yeah. So this is the airbag. This is the capsule, and this is the view looking down the whole channel, whole tube from the top. Yeah. Okay. So let's see what happens. Okay. So see how the airbag is deflating. Yeah. Let's play this once more. It drops down all the way down. So So during this drop here, somewhere in the middle, we get 2.5 seconds of microgravity. So whatever experimental setup I have to do, I have to collect the data in the 2.5 seconds and see what happens and study the phenomena in that process. Yeah. Okay. So there are more visuals here. I'll just play this along while I'm talking here. So you can see the different camera viewpoints here. This is the control room. This is a close-up of the airbag here. So right now it happened very fast here. I'm just going to play this again. Yeah. This is not a slow motion video. So you can see it's dropping down here. You can see at different points where the camera captures this capsule falling down. Yeah. Okay. So control room is down here. You can get data and see what happens. Of course, you have to go down here to the bottom and retrieve the unit. Okay. Okay, so we've done some fun experiments as part of this drop tower testing and so on and so forth. So I'll just show some videos here. So you can see this is actually a mixture of, as it says here, metal nuts, metal balls, polystyrene balls, and paper shreds. Yeah, so they're of different weights, as you can see here. So let's see what happens during the drop. So this is this whole jar was inside the capsule and it was dropped from the top. So somewhere in the middle, you'll get 2.5 seconds of microgravity. And that the microgravity that's all you can get, 2.5 seconds, and that's what is 2.5 seconds all about. Yeah. Okay. So we have that's kind of a time interval is always available to do an experiment. Okay. Yeah. So this is the kind of experiment facility we have recently set up in our campus, and it's available for our ExTeM group to use. Yeah. Okay. Okay, so there have been some flame experiments work that's been done. So here is an example of a flame experiment. So there's actually a tissue paper here. You start the flame at the tissue paper by using a hot wire arrangement, for example. And then you kind of study what happens to the flame as it travels down here, for example. Yeah, okay. So this kind of experiments can be done. You start the flame, you drop the whole capsule into the tube and see what happens to the flame at different stages of the arrangement. Yeah, so you can see, right? So there's a very small interval at which the 2.5 seconds happens, and your flame behavior can be studied in this fashion here, for example. I'll show you some more detailed pictures a little bit later. Okay. Okay, so here's your more still pictures. So we actually have a camera that is observing the whole thing. So the whole camera, everything drops down along with the capsule itself. And you can get this kind of picture. So here is normal gravity, what happens. Here's microgravity. The flame is almost extinguished here, as you can see. At the point of impact, you get a high G here, so you can get a different pictures. So this is a kind of facility that's available for us to use to simulate microgravity in our campus here. Right? Okay. So based on this, for the ExTeM group, we have right now 5 drop designs going on. So for example, we are looking at microplasma arc transfer. So if you have to do 3D metal 3D printing, we need to understand what happens to the plasma and how the transfer of the metal drop happens, for example. So that is something we are working on. And we also have another setup that's studying machine tool structures. If I were to use a machine tool in space, or how's microgravity affecting the dynamics of some of these machine tools? So we have a setup that's going on there. We have a micro OG setup for metal foaming. I'll talk a little bit about that later. And also about diamond growth. So we're trying to grow some diamonds as well and see. Of course, it's the small time scales are very challenging. We'll have to see what kind of even if it's nanometric growth, we can probably see it. So we are doing a setup on that. And finally, a 5th setup that is going on in polymer printing as well. So it's again 3D printing, but more on the polymer side. Yeah, so both metal and polymers we are looking at as well. So these are the 5 setup designs that that's ongoing right now. We're hoping that sometime in the near future we'll have some results to show as well. Okay. Besides this, we're also exploring some parabolic flight options for us to consider. So parabolic flights, as I mentioned earlier, you get slightly longer durations. From seconds, you can go into minutes, tens of minutes, maybe 10, 15 minutes, something like that. And sorry, tens of seconds. Sorry, not minutes. Tens of seconds here. And you can be next to your setup right there, and then you can actually switch on stuff, and see. So here's an example of a commercial. This is actually in Europe. Airbus system has that, but then you have a commercial player in the US as well. So for example, this is a US commercial company, 0G, that offers, so you have an empty space in your aircraft. You can actually rent this space. It costs about $40,000 for a 5-flight package. And they have all kinds of packages available. there are many people who have made use of this kind of systems to do this. So commercially, also some options are available for parabolic flights, which right now we will not make use of it, but we will do the drop tower facility experiments first. We'll move to this at the next phase, so to speak. Yeah. Of course, it'll also be nice if this option is available in India. And if you see what does it take to make parabolic flights, if you see, you basically need a plane like a Boeing 727-200 or so. There are some modifications that are needed for the hydraulics because of the way the plane climbs very steeply and comes down. And you need to have accelerometers on your dashboard, which is not normally available on a commercial flight. Of course, you have to remove all the seats. You have to add paddings all around because you don't want to be bumping into hard metal. You need to get door access from the tail end. There are no doors on the sides, only the tail end. You go inside with all your setup. Of course, you have to get flight certified. And if you're a commercial company, you have to sell flight time and make money. And we're hoping that some Indian company will take this up as well. I'm talking to a few people, but it's a tough industry to be in right now for airline industry. Of course, you have to lease the plane, airport charges, running costs, maintenance costs, and so forth. So if we're exploring to see if there's any interest in India for these parabolic flights, mainly because our commercial options outside India is very expensive, which we cannot afford right now. Okay, so that's all about what is ExTeM. I told you about. We talked about microgravity. What are things that microgravity affects? How to get it on Earth. So I'll spend a little bit of time now on the aspects of what we are trying to do here in making space for space and making space for Earth. I have about 10-15 minutes or so left. So I've picked a few projects only because some of them are still ongoing. I can't talk in too much detail yet about these because these are projects in progress or just initiated actually. Yeah. Okay. So I picked two projects for making space for space. So what is making for space again? We are trying to make stuff in space for space use itself. Yeah. Okay. So one of the projects that my colleague Piyush Chansali from the Civil Engineering Department is trying to do is he's trying to make space concrete. Yeah. I mean, we all know about concrete on the Earth here, right? It has a lot of ingredients. You mix water, it sets, and you can make buildings and structures out of it. Yeah. Okay. Of course, the raw material for the Earth-based concrete comes from the Earth. We dig up, we get all these, this blue metal, so to speak, those little stones, the cement, everything comes from the Earth. Again, we prepare it, and you have to mix it and make it into the right proportions and so on and so forth. But when you go to Mars or when you go to Moon, we have to figure out how to make use of the material that is already there. Yeah. Okay. So of course, India has not landed any systems yet on Moon or Mars, but people have landed in the past. Many countries have now been able to. In fact, we have two rovers right now on the Mars itself. One is from US, one is from China, and they have brought back samples. Yeah. And based on the samples, we have actually made, able to make simulated samples that look like that, because we know what the ingredients are in the samples that came back from Mars and Moon, and you can actually buy those simulated materials. Yeah. Okay. So right now we have we just got about a couple of weeks back some because of regolith simulants. Okay. So we have received that, and we are now doing some tests. Piyush and his team are now doing some testing on that. And then the challenge there is, you may have material that's available in Mars or Moon, but there's no water available. Yeah. So where this water is going to come from? Yeah. So what Piyush is trying to do is how we can consolidate these materials without water. Yeah. So we're talking about waterless concretes that can be made. Okay. So he's going to make some of these. He is going to try different recipes. Of course, he has to add some few things. We'll have to figure out what to add and where the material is going to come from as well. Okay. And then he's going to do that, and then he's going to assess strength and durability of this kind of space concrete at varying temperatures as well. So one of the challenges in being on Mars or Moon is the temperature variation is substantial. When the sun is shining, the sun is not shining. Because of the limited atmosphere that's available, Mars has some atmosphere, Moon has literally none. So temperature variation is very wide. So you have to figure out whatever you make has to be able to withstand such temperature variation, temperature shocks. So he's going to. So Piyush's group, as part of the ExTeM projects, is going to work on space concrete using the simulants that's available, and then assess the strength and durability of these at various conditions as well. Yeah. Okay. So this is something that is an exciting project that is going on, and we just received the simulant, as I said, and we're playing around with it. Okay. The second one related to making space for space is use of unmanned drilling robots. Eventually, at some point of time, when India figures out we're going to have something on the moon or the Mars, we're hoping that we'll be ready with a solution for this as well. So you're able to not only just have a robot that's going around, but we are able to actually drill or remotely controlled drilling unit as well that's mounted on the robots. Yeah. And if you look at our campus, we have, as you know, the Center for Innovation C5 teams. There's several student teams that are looking at making robots, unmanned robots. There's Team Anveshak, there is Team Abhiyan. Yeah, so they're all looking at unmanned systems. Okay, so what we are convinced one of the teams is look at is incorporate build and incorporate an automatic drilling unit into these robots or the rovers. Okay, so that's something that is ongoing. The major challenge in such remote drilling, of course, is first of all you have to remotely control it. There's no immediate feedback that's coming from systems. You need to have a drill bit that is it has to have sensors in there. It has to figure out, hey, am I drilling in a hard spot here, a rough spot here, or a soft spot here, or so we can change the drilling conditions, or even choose the drill bit properly depending on what is available there at the place to drill. Yeah. So these are some of the challenges here. Of course, there are rebounding forces, so your rover has to be able to give a reaction force to the drill. Yeah, and there's a lot of sensing involved. So we're looking at some waveguide ultrasonic sensing to figure out how to give feedback to the drilling process, and everything has to happen in situ at the control unit. There's no, you can't have an 8-minute lag to the earth and then come back with a feedback signal. That's not possible. So that system has to be intelligent enough to figure out what to do in that as well. Yeah. Okay, so this is something that the team Abhiyan has decided to take it up, and we are having some communications with the team. Of course, the pandemic has created a few challenges to get some of these things, going. But we're hoping that soon we'll be able to work quickly on this. Okay, so these are the two things that are happening in terms of the make in space for space. So space-based concrete, and then you have this unmanned drilling robot systems. Okay. The next one that I want to talk about is making space for Earth. That is, we want to make materials, certain materials that are amenable for making better in microgravity conditions, and then bring them back here in the Earth and see if you can actually get better structures, material structures, especially for that. And in that, there are two projects that I'll talk about. One is the metal foam, another one is diamond growth as well. Yeah. Okay, so metal foams. So we all know about sponges, right? Sponges is as a foamy structure, as you can see here. So this is actually a polymer, and you can see there's a lot of huge holes in the polymer structure. Yeah. Okay. So because of this, it's able to wick water and use it and so forth, and also lightweight. Yeah. And the entire polymer is lightweight because of this. Yeah. Okay. Now imagine a sponge like this, but made in metal. Yeah. That's what we mean by metal foam. Okay. So this structure, we are actually able to make in metals also. Yeah. So this is metal foams. And these are some of the foams that are made in our labs here. So we have, this is Professor Shankaran's lab. He's with the Department of Metallurgy and Materials Engineering, for instance. Yeah. Okay. So here is you can see the open foamy structure here as well. Maybe I can probably zoom in a little bit to show you. So here it is. So you can see the foamy structure here. So you can see the foamy structure here with the blowholes, etc. Same thing you can get in a metal. This is actually an aluminum alloy. Yeah. So you can see the difference between the solid where there's no foam here and there is a foam here, for example. Yeah. Okay. And here's a picture of a CT scan. So just like how we do CT scans in our health centers, medical facilities, etc., you can do CT scans with these guys as well. And you can actually get a precise location of a particular foam. The entire 3D model can be made as well. Yeah. Okay. So we put the sample into a CT scan center, which machine we have here, the machine design section, and you can actually get a complete picture. You can actually slice it at each position and see without actually physically having to destroy your sample, and see where the particular pores are, for instance. Yeah. Okay. So this is something that is already ongoing. We can actually make these metal foams on the Earth here. Okay. But there are significant challenges in this, and the way these metal foams are made, you actually melt aluminum. Okay, you have molten aluminum. Imagine molten aluminum, but when we put some stuff inside, that will actually create gases inside. Yeah. Okay, so we add, TiH2, for example, or other particles inside, which will actually release this hydrogen gas. Okay, and forms a bubble. Yeah. And this bubble will start floating around. There's buoyancy effects. It'll start moving around inside. And gravity influences this a lot. How the bubbles form, the expansion rate of the bubbles, and so on and so forth. So these the gravity influences some of these foam formation so much that it actually inhibits these foams from forming in several materials. Yeah. Okay, and that's why we think that microgravity can have a significant effect on this. You can actually switch off gravity, so to speak, and then study what happens to these bubbles as they form, and the rate of change of this expansion of these pores, so to speak. We think that there's a lot of advantages in doing some of this foaming out in the space there when there is gravity is very low. Yeah, you form the material there, you create a nice foam, bring them back into the earth, and use them for whatever you want. Okay, so that's sort of what we are. And we're not the only ones who think about it here. There are some people have already done some work on this. So you can see here, this is actually bulk metallic glass foams that have been made in space. Yeah. So BMG stands for bulk metallic glass. Yeah. So normal metal is crystalline in structure. This particular metal is actually in an amorphous state. Crystalline means there's a lot of order in the metals, whereas amorphous state means there's not much order in the system there. Yeah. Okay. Creating foams in these bulk metallic glass is very difficult on the Earth. Yeah, because gravity doesn't allow this expansion of foams to happen inside the structures. So if you switch off gravity, there's a lot of possibilities of creating foamy structures in bulk metallic glass. Yeah. Okay. So here's an kind of experiment that people have done before. They're trying to have a heat source, and you have a small sample here. These are very small samples. You can see it's very small samples. They've been able to make small metal foams. Yeah. Okay. So there are different kinds of bulk metallic glasses. So we are trying here a particular type of bulk metallic glass to see if we can actually use that to foam. Yeah. Okay. Why BMGs? That's explained here. They have high viscosity, and there's something called the sedimentation velocity for the bubbles that are used to make the foam. And they're very small compared to aluminum. So now 1 nanometers per second versus 1 meters per second. So very very large orders of difference. Okay, but BMDs have high strength, toughness. In fact, they're being investigated for high performance load bearing applications. Okay, and if you can actually foam it, you can actually reduce the weight, and then so they have a lot of advantages as well. And there are also other consumer products which you can make. In fact, they already made bulk metallic glass. Those. If you used a USB long time back, you must have used a USB with a cover. Some of those covers are made of bulk metallic glass, for instance. But consumer electronics, jewelry, fuel cells, coatings, they all have a lot of advantages in this. Okay. So again, I'm explaining more about why BMGs, packing them into a small launch volume and then use it to fill up a mold and free expansions, etc. Mainly for energy absorbing capacity is a major advancement that's required for space manufacturing. Okay, so there is another process called rapid discharge forming that's been demonstrated, and you can actually form BMG in very, very fast. Okay, and if you can actually combine some of this with your micro G and your foaming ability, then it has a lot of advantages in making this bulk metallic glass foams. Okay, so that's the advantage of this. Okay. The second project that's going on, one of the many projects actually, but I'm just showcasing only two. So I showcase the bulk metallic foam. So we're building a setup for that. Another setup that we're building is for CVD diamond coatings. Yeah. Okay. So the reason why the use case for this is something like this. So if you look at the current method of generating water on board a space flight, like International Space Station, for example, they use something called as the Sabatier process. So I'm going to zoom in here a little bit so that we can see. So the current method of generating water on board is called as the Sabatier process, and it actually produces methane as a byproduct. Yeah, and hydrogen is also available. So methane and hydrogen both are available, and people don't know what to do with it. They don't want to simply release it back into space. They actually collect it now and then see if you can reuse it. Yeah, and one of the ways you can actually reuse methane and hydrogen is actually you can use this to create diamond. Yeah. And we actually have a machine here. This is a machine in our lab here, which actually does that. It actually takes methane, it takes hydrogen. So you can see all these pipes coming here that you can supply methane hydrogen into. This is the chamber, and inside this chamber here, you can see this chamber is open here. You can see this here, and inside this chamber we have this. Imagine an incandescent bulb. The bulb that is no longer in use today. You have a tungsten filament there, yeah, that gets red hot, and you get light from the bulb, right? So something like that is what we use here. You have the straight tungsten filament rods. Yeah, it's not rods, actually wires, very thin wires. About 31 of them here. They're heated to over 2000 degrees Celsius, and you feed in hydrogen and methane inside here. And whatever substance you put at the bottom, you can actually grow diamond on top of it, because it breaks down the carbon. The carbon comes down, actually grows, and then becomes a diamond structure under certain conditions. You have to have a right recipe for that. Yeah. Okay. So what we said, okay, this is available on board. Methane hydrogen is available. So why not we make use of it and see if we can actually build a HFCVD reactor that we can use in space. Yeah. And of course, here there is on Earth. Here, this is the lab setup on the Earth. Here there is a strong gravity effect. So diffusion of how the carbon diffuses, etc., is influenced by gravity. Yeah. So now, if you go into microgravity, what happens with the diffusion helps us. With the diffusion doesn't work with us, etc. We want to find. So we're trying to build two setups here. One setup will simply look at some very fundamental phenomena related to this. What I'm calling setup A. It's still in the design stage right now, so I'm not able to show you any pictures. And we want to build a setup B, which will actually grow these diamonds as well. Yeah. And of course, we right now we only have 2.5 seconds, and these are very slow growth rate processes. But within 2.5 seconds, even if I get a nanocrystal formed, for example, I can still be able to look at it in an SEM or an electron microscopy, and still be able to understand what is going on in terms of the growth process. So we are hoping to do that. Of course, if we want to slowly move on to a parabolic flight system as well, so we are working towards that right now. Yeah. Okay. And sorry, I didn't explain what is CVD. CVD is V stands for vapor deposition, chemical vapor deposition. So we are depositing from a vapor state and growing crystals, and such as diamond, for instance. Yeah, that's basically what we're doing here. So we want to do a drop tower. We want to go into parabolic flight as well. So this is sort of one other project that is going on. Yeah. So in this case, I showed you two case studies. One is for foaming metals, especially bulk metallic glass, and this one is about growing diamond crystals and studying the effect of microgravity on it. Okay. Okay, so we have come to the end of this year. I'm also exceeded the 45-minute limit here, so I'm going to quickly finish it up here. So so where are we at with what the world is doing? Obviously, so the answer to that question is we are a little bit behind. India, when I say we, means India, also IIT Madras here. So NASA, the European Space Agency, Japanese Space Agency, Russian agency, and now China as well. They are all planning for a lot of things: lunar Mars, asteroid mining, settlement bases, etc. ISRO is also doing a lot of this planning as well. And I have to be honest, many manufacturing processes have already been tested in the International Space Station. The ISS, we don't have access to ISS. India doesn't have, but you can get microgravity in ISS for long periods of time. Yeah. But even there, they have other constraints, space constraints, energy constraints, and so forth. But people have managed to do some testing of 3D printing. Machining has been done on a parabolic flight, for example. The good old workshop lathe machining that you guys did in your study here at the workshop, that machine, one aspect of the machine went on a parabolic flight, for example, have been tested. Okay. And NASA is planning a low Earth orbit economy. So imagine factories in space. Elon Musk's rocket takes raw materials to the factory there. They convert it to material, comes back down, they sell it down on the Earth. Yeah. So there's some commercial angle also is being looked at. And as you know, there's a lot of commercial players now. India is also trying to encourage commercial players in not just for transports in space, but also other things such as making these optical fibers, making diamonds, and so on and so forth in space. So to this initiative, it's a small initiative we've just started here. We hope to remain competitive in this, and then see if we can actually do things a little better as well. So this is our team. I'm not alone in this. I'm only coordinating this whole center. We have a team from mechanical engineers, we have aerospace engineers, we have chemistry people, we have materials and metallurgical engineers, physics, MSIs from physics. And then we also have external collaborators. We have Divakar, who's coming from the GNA CSR Center. We have international collaborators as well. We are trying to partner up with some startups as well, including from the US, from Space Foundry, E-Plane, and FabHead for our Indian startups over here. This is our team. So I have to acknowledge all these people, efforts in writing the proposal, kickstarting various projects. The team is continued here, different faculties, they're all faculty here. And we have hired some people as well. So Niket is with us, Venkat is with us, and Dr. Aditya has joined us from Singapore, he's here. And we also have one more lady who's joining, Priya. I've not shown her picture here, she's just about to join. And we're also thankful to our collaborators who are exploring some of these options with us as well. Yeah, okay. As are some external collaborators, industry collaborators. Divakar is one. We have Dinesh, Ram Prasad, and so on and so forth. Okay, so I'll stop here. Thank you very much. This is a Photoshop picture of us floating around in a parabolic flight. I'm hoping that by next year this will be a reality, and I'll be able to show you a real picture of us floating around in space as well. Okay, so thank you very much. Yeah.
Yeah, so thank you for really good session. Yeah, that was really interesting hearing about space, especially as a space enthusiast. And I hope everyone enjoyed the session as well. So I think let's move on to the question and answer session.
Okay.
So yeah, we have a couple of questions here. First one is: are there efforts to make use of old mines like the Kolar gold mine for microgravity experiments? They can be a couple of kilometers deep. So,
Yes, there is. Our group is not involved, but there is some efforts that ISRO and team are looking at to see how the long mine shafts that are available in defunct mines can be used as for a drop as well. Yeah. So some efforts are ongoing. I have to be honest, I don't know the full progress that's happening in that. But even that will actually only give you a few more seconds of time. Yeah, it won't give you the luxury of large minutes, etc. But yeah, it's definitely better than a 2.5-second drop. And there are teams that are looking at it and exploring such options in India as well. Yeah.
so the next question is 3D printing possible in microgravity?
Yes. 3D printing is definitely possible. There are some challenges in doing 3D printing under microgravity, obviously. So, for example, if you think of 3D printing, one way is you use powders. You use small powders and you melt those powders and it falls down, right? So, first of all, powders difficult to handle in space, yeah, because powders can easily sort of go away, yeah. And even if you melt metal, it has the way it drops down onto the substrate where you're depositing is also a challenge, yeah. Okay, in fact, we are actually studying that phenomena right now in one of the setups, yeah. And of course, the other thing that is complicated in space is, if you're using lasers, etc., there's a lot of safety issues. Energy involved is very high. Yeah. So what we are doing, and what some people are also trying to finally narrow down to, is your regular welding process. Some of you alumni must have done some welding shuttle workshop, right? So that welding process actually has a wire, and then you're simply using high current, and then there's a plasma at the end to drop the bead. That kind of process is what people have dialed down to right now for 3D printing, for metal 3D printing. Yeah. So that is being investigated, and we are also investigating that here right now. So we're building a setup for that investigation, for example. So yes, 3D printing is entirely possible in space. Yeah.
So the next question is ExTeM IITM collaborating with ISR?
Okay. Yes. In fact, when we first started the proposal itself, we had sent the copies to ISRO. ISRO is interested. They want us to first prove ourselves, so to learn a few things first. So we are going to use the current funds that we have from IIT Madras to learn and get some experience and showcase a few things. Then we will really knock on ISRO's door and see if we can convince them to actually invest in us. Yeah. So there is some communication going on between ISRO and ExTeM. Right now, ISRO is in a sort of a wait and watch mode. They'll say, okay, can you guys really do stuff I want to see? So we are hoping to prove ourselves first, and then we'll go to ISRO as a full-fledged mode. Yeah.
Yeah, also on the facilities one, I had a question like, what about the drop tower experiments? Like, how important is getting a longer period of microgravity in your research?
Oh yeah. See, definitely, we would like to have hours and days and weeks of microgravity if that's possible. Yeah. So, for example, the diamond growth that I'm talking about, I really need about 8 to 10 hours to grow diamond properly. Yeah. So definitely, hours of microgravity would be a luxury to have. Unfortunately, we have only a few seconds right now. I can maybe go into tens of seconds with a parabolic flight. But getting good microgravity for a long time is priceless. I mean, there's nothing like it. Yeah. But right now, the only option that I have is, there's something called as a PS4 platform in ISRO, where they will launch something as part of the regular satellite launch vehicle, and that will go around the Earth for some time. Yeah. So we could put a setup there, and but only thing is space is very small, energy is very small there as well, available, and it will actually destroy itself after some time because it will just come back into the Earth. Yeah. So that's the only option we have right now from India. A space station is, of course, would be nice to have, but we don't have access to space station unless India launches its own space station. But yeah, having microgravity, long times of microgravity is, is something we really want right now. But there's a lot of challenges for that. Yeah.
So yeah, I think that's it from the question and answer session, sir. So yeah, thanks a lot for organizing this session. Yeah, I want to thank. Okay, there is one more question here from Pranav Rai. What is the quality of the diamond made with this?
We have not
It's
yet made
about
it.
growing diamond.
Yeah, we're still growing it. We are expecting better quality because the diffusion process, the way the carbon atoms come and settle down and causes the diamond to grow, will be much better without gravity influencing it. Is what we feel. So we'll have to see. I'm hoping I can report on this sometime next year with the experiments done.
Yeah, there's one more question. Yeah. So, what are the areas of interest or products for the collaboration with ISRO?
What are the areas?
Products,
Yeah. Okay. So
and the
right
products.
now,
Yeah.
yeah. See, right now, what ISRO, of course, ISRO is right now busy trying to launch Indian astronauts into space. Yeah. Okay.
Yeah.
So they are very keen on working on, for example, inside their, they're going to send people there. People are going to spend some time on a space flight, right? So whatever is required for the safety of the people in the space flight, anything that they can make on their own there, including 3D printing processes, etc., is something of interest to them. Yeah. So in that sense, there is some overlap between what we are planning here and what they are trying to do right now. Yeah. Okay. So the human spaceflight program, which they're having, the manned spaceflight program, has a lot of overlap with what we are doing. Yeah. And they want they're expecting a lot of support in that direction. Right now, we are not fully ready yet because we're just getting into it, but we are hoping to support ISRO much better at a certain later point of time. Yeah.
Yeah. Okay. Yeah, I think that's it from this answer
Okay. Great.
session. I don't find any other questions here. So yeah, thanks a lot, sir, for taking this time to explain one of the more really exciting researches going on, which is great to hear as a fresher as well, coming to the institute and not having seen it. So yeah, hopefully we can meet some time else. And yeah, I want to thank the audience and IIT Mark for organizing such a session. So thanks.
Okay. Great. Thank you. Thank you. Thanks to the alumni office team and also all the alumni who are watching this. Thank you very much for the opportunity. Thank you.